Everyday mathematics. Today we shift gears and move forward to the regular season set of questions, problems 11 to 20 of the 2025 MIT Integration B. Problem 11 happened to be the indefinite integral of the square root of x plus nested within the square root of x squared minus 1. Problem 12 was the indefinite integral of x cubed minus x over x to the power 6 minus 1. Problem 13 was the indefinite integral of the square root of x squared minus 1. Problem 14, the indefinite integral of sine of x times sine of x times the sine of cosine of x plus the cosine of x times cosine of sine of x times cosine of x. Problem 15 happened to be an indefinite integral of the square of the natural logarithm of x over x. Problem 16 was also an indefinite integral of the square of sine 2x times e to the power 2x. Problem 17 was the definite integral from x equals to 0 to x equals to 7 over 2 of the square root of x plus 1 over the square root of x plus continuing, so nested square root all the way. And then problem 18, an indefinite integral from x equals to 0 to x tending to infinity of the fourth power of x plus 1 times e to the power negative x squared. Problem 19, a definite integral from x equals to 0 to x equals to pi over 2 of cosine 3x times cosine 5x times cosine 7x. Problem 20, an interesting problem, a definite integral from x equals to negative 1 to x equals to 1 of e to the power 2x times sine of the hyperbolic sine of x. So really interesting problems. I hope you stick around and see how we may be able to solve these problems. We're going to look at two methods to solve this problem 11. The first problem would entail substituting for the entire expression in the integrand. And I'll begin by saying let u be equal to the square root of x plus the square root of x squared minus 1, so that when you square both the left and right hand side, you get u squared equals to x plus the square root of x squared minus 1, and then you pull x onto the left hand side, this x here, so that you have u squared minus x equals to the square root of x squared minus 1. What that means is now you could square both the left and right hand side, and so you get u squared minus x all squared equals to x squared minus 1. And you could see where I'm trying to go, because now when I expand the left hand side, I have an x squared both on the left and right hand side. Those cancel each other, so that eventually we do have u to the power 4 minus 2x u squared is equals to negative 1. Take the negative 1, add positive 1 on both sides, so that you have u to the power 4 plus 1, and then when you add 2x u squared to both right and left hand side, you get 2x u squared onto the left hand on the right hand side rather. And so dividing both sides by 2u squared means that now we have u to the power 4 plus 1 over 2u squared equals to 2x. And you may as well go ahead and divide the individual items in the numerator by 2u squared. So we have half u squared plus 1 over u squared equals to 2x. So differentiating both sides with respect to x, we have a half of 2u minus 2 over u to the power 3 du dx equals to 1. And that means that we could now say that half times 2u minus u over minus 2 over u to the power 3 du can be used to substitute for dx. So now going forward, we had intentionally substituted the entire integrand with u, so that is u, and our dx we found was a half times 2u minus 2 over u to the power 3 du. So when u propagates through, what happens is we have, and then obviously half cancels the 2 here, so we have the integral of u squared minus 1 over u squared. And that is easy because we have now u to the power 3 plus 1 over u plus the integration constant. You could simplify the expression in form of u so that we have u to the power 4 plus 3 over 3u. Now, important thing, since we had set u to be equal to the square root of x plus the square root of x squared minus 1, what we can do now is plug in where u is with x plus square root of x plus square root of x squared minus 1, and this is easy. We can simplify it further, but I could just leave the expression the way it is. I mean, if you're curious and you're obsessive, you could go on, but this is one of the ways that obviously you may be able to solve this problem. Yeah, expanding this part here, you get what we have here, and you can continue making things easy. So you have 2x squared plus 2x square root of x squared minus 1 plus 2 over 3 times the square root of x plus the square root of x squared minus 1. So I would choose to stop here because I think this is a fairly simplified expression. The second method is obviously different. What I would do is I would choose to express x as the sum of x plus 1 over 2 plus and x minus 1 over 2. And then under the square root sign, this is simply a difference of 2 squared. So you have x squared minus 1 being x plus 1 times x minus 1. And that means that we do have a quadratic in play under the square root sign. So that means we have the square root of x plus 1 over 2 and x minus 1 over 2 when added, because there's a hidden 2 there. But let's just go ahead and show that explicitly. So there's a 2 here, and there is a product of the square root of x plus 1 over 2 square root of x minus 1 over 2. So what that means is that we do have the square root of the square of x plus 1 over 2 plus x minus 1 over 2. So the square under the square root sign gets cancelled out by the square root, so we eventually just have the integral of the square root of x plus 1 over 2 plus the square root of x minus 1 over 2. We can pull out 1 over square root of 2, so now we do have the square root of x plus 1 plus the square root of x minus 1. And those are easy integrals to solve, because with this we do have 2 over 3 x plus 1 to the power 3 over 2, and then with this part here we have 2 over 3 times x minus 1 over 3 over 2, and obviously the constant 1 over square root of 2 applies, and when you simplify this it becomes a root of 2 over 3 times x plus 1 to the power 3 over 2 plus root 2 over 3 times square root of times x minus 1 to the power 3 over 2, obviously plus the integration constant. And so that is how you may be able to solve these problems. There are two methods. I believe the expression here and the previous expression are similar. The difference could just be a constant. So problem 12 is fascinating, and this is, I think, was a test on whether somebody is able to do long division. So what I could do here initially is pull out the x, so we have x squared minus 1 over x to the power 6 minus 1. And so in a way, I think within x to the power 6 minus 1, there is a factor of x squared minus 1. And to prove that, we just go and use long division. So we have x squared, x to the power 6 minus 1 divided by x squared minus 1. And so when you multiply by x to the power 4, you have x to the power 6 minus x to the power 4. And you subtract that from whatever is the x squared minus 1, we get x to the power 4 minus 1, and then you multiply x squared with x squared minus 1, we have x to the power 4 x to the power 4 minus x squared, and so the difference there is x squared minus 1, and then you multiply by 1, and so you have x squared minus 1, and the remainder or the residue there is 0. And so what that means is that x to the power 6 minus 1 in the denominator is the same as x squared minus 1 times x squared plus x squared, x to the power 4 times x squared plus 1. Obviously, the x squared minus 1 in numerator and the x squared minus 1 the denominator cancel out, so you do have x to the power x over x to the power 4 plus x squared plus 1 in the denominator. We can re-express whatever is in the denominator as x squared plus half squared minus, to remove the square over half, we have minus a quarter, plus obviously this 1. So this means that now we do have x over x squared plus a half to the power 2 plus 3/4. And 3/4 comes from this negative a quarter plus 1. And so we can use the substitution with the tangent. I could say let x squared plus a half be equal to the square root of 3 over 4 tangent theta, which is the same as root 3 over 2. And so we have 2x dx d theta being equal to root 3 over 2 sec squared theta. That implies that x dx equals to root 3 over 4 sec squared theta. And that now would allow us to substitute, because in the numerator we already have x dx, and so we just plug in the root 3 over 4 root 3 over 2 tan theta here, and the numerator in place of x dx we have root 3 over 4 sec squared theta. So those allow us to now pull the root 3 over 4 in the denominator out, and also the constant in the numerator comes out. So essentially you have the integral of sec squared theta over tan squared theta plus 1. Now tan squared theta plus 1 is the same as sec squared theta, and that means that we can now simplify things. The quarters obviously numerator and denominator cancel, and we have root 3 over 3, which is the same as 1 over root 3, and the sec squared theta in the numerator and denominator cancel out, so you have the integral of 1. So we have 1 over root 3 theta plus integration constant. But since we had substituted for x with x squared plus a half being equal to root 3 over 2 tangent theta, that means that 2x squared plus 1 over 2 is the same as root 3 over 2 tangent theta. The halves on both sides cancel each other, so you have 2x squared plus 1 over root 3 being equal to tan theta, and therefore theta is the arctangent of 2x squared plus 1 over root 3, and we can plug that back, and that allows us to now see that the integral of x cubed minus x over x to the power 6 minus 1 is equals to 1 over root 3 arctangent of 2x squared plus 1 over root 3 in place of the theta we had plus the integration constant, and that was the answer that was being sought for. So on to problem number 13, the indefinite integral of the square root of x squared minus 1. There are, I think, two ways to go about it. One of the ways I chose was to just know that use the integration by parts route. You could also choose to say let x be equal to the hyperbolic sine of x of u or something like that, and still be able to get the answer. But just trying to use a different method here. The hidden one here is the same as the derivative of x, and knowing that when you have integration by parts as a strategy, when you have two functions v and du being integrated, that is same as uv minus the integral of u times dv. And so in our situation here, we have capital U as dx and v as the square root of x squared minus 1. And that means that now our integral is uv is x times x squared minus 1 minus x times the derivative of square root of x squared minus 1, which is the same as x times the square root of x squared minus 1 from here, minus the integral of x times a half, the derivative of whatever is under the square root sign becomes a half of 1 over square root of x squared minus 1 times the derivative of 2x, which is 2x. So the 2's probably cancel, they do cancel out. And so we have x times the square root of x squared minus 1 minus the square of x squared over the square root of x squared minus 1. And so we can play around with whatever is in the numerator here. X squared is the same as x squared minus 1 plus 1, so that now you have x times square root of x squared minus 1 minus the square root of x squared minus 1, because this is the same as the square of x squared minus 1. So 1 of the square root of x squared minus 1 cancel with whatever is the denominator, minus this 1 over square root of x squared minus 1. So this here is the same as I, where we started from, and on the left hand side we choose to have I as the initial integral, and you bunch that up so that you have 2I is equals to x times the square root x times the square root of x squared minus 1 minus the integral of 1 over x squared minus 1, so that I is the same as half of x times x squared minus the square root of x squared minus 1 minus a half the integral of 1 over square root of x squared minus 1. So this is a famous integral. You could choose to also use a hyperbolic sign and play around, but we know that the integral of 1 over square root of x squared minus 1 is the natural logarithm of x plus the square root of x squared minus 1, if plus obviously the integration constant. If you need us to prove how this comes to be, please leave a comment in the comment section and we'll be able to show you that. So what that means is the initial integral is half x times the square root of x squared minus 1 minus half the natural logarithm of x plus the square root of x squared minus 1 plus the integration constant. And that was the answer that was being sought for. You can just now sum up things and say, okay, the integral of x squared, the square root of x squared minus 1 is the same as half times x times the square root of x squared minus 1 minus half the natural logarithm of x plus the square root of x squared minus 1 plus the integration constant. So problem number 14, interesting. I think this was just a play with the expression, trigonometric expression. We can choose to look at one of the expression and lock it as a derivative. So I see sine x here, and this comes from differentiating a cosine x somewhere. So I would express this first expression as the sine x times the sine cosine x times the derivative of negative cosine x, And this cosine x is a derivative of sine x, so I'll just say this is the same as the derivative of sine x times cosine of sine x, cosine of x. Now we can still go further and say bunching this and this, we get the derivative of cosine of x. So, and the negative obviously fizzles out because we have a nested cosine there. So we have now sine times the sine of x times the derivative of cosine of x plus, and again we do the same thing here by bunching these two. So we have the derivative of sine of x times the cosine of x. Now we begin to see the derivative of a product here, because this cosine of x is what is here, and then the derivative of sine of x, the sine of x is still here. So when you have a product of two functions uv, and then you differentiate that, that's the same as one function times the derivative of one plus the other function times the derivative of the other, and that's what we see here. So now we get just we can now express this as the derivative of the product of sine of x and cosine of x, and that allows you now to see that you have a derivative under the integral sign, an integral being an antiderivative, so the procedures cancel each other, and so we are left with just sine of x times cosine of x as our answer. And the integration constant obviously is not to be forgotten. So let me grab a cup of tea a little bit, but on to problem number 15. The integral of the square of natural logarithm of x over x. Let's just expand whatever we have here. So this is the same as the square of the natural logarithm of x times 1 over x squared. Now 1 over x squared is the same as the derivative of the negative of 1 over x. The negative of 1 over x, yes. And then we can use integration by parts, our popular expression where if you have a product of v and the derivative of u, and you integrate that, you get uv, product of u and v, minus the product of capital U and the derivative of v. So our u happens to be negative 1 over x, and so our uv is going to be negative natural log of x squared over x minus under the integral we have negative 1 over x times the derivative of the square of the natural logarithm of x. So we have negative the square of natural logarithm of x over x plus the negative here and the negative here interact. 1 over x, differentiating this, we first of all get 2 the natural log of x times the derivative of natural log of x, which is the same as 1 over x. So that 1 over x here will interact with this 1 over x eventually, and so we can now go forward and bunch those together so that we have negative the square of natural log of x over x plus, pull the 2 out, the natural logarithm of x over x squared. Again, 1 over x squared is the same as the derivative of the negative of 1 over x, right? And then we repeat the same process of integration by parts, where our uv will be twice the negative of 1 over x times the log of x, and then minus twice negative 1 over x times the derivative of log of x. And so the log of x differentiated is the same as 1 over x, and obviously this negative and these negatives will interact, and so we have plus here twice 1 over x times 1 over x. This becomes an easy integral now to solve, because now we have the integral of 1 over x squared, which is and there's obviously a 2 here which we had forgotten, which we need to remember, and so we have 1 over x squared integrated is negative 1 over x, and the integration constant obviously needs to be remembered, so we can pull out the negative across all these expressions, and we have negative of a fraction that involves the numerator being the square of natural logarithm of x plus twice the log of x, natural log of x, plus 2 over x plus the integration constant, and that was the answer that was being sought for. To problem number 16, the first thing is the square of sine of 2x. I think we want to express that through a double angle formalism, and that we could use cosine 2a being equal to 1 minus 2 sine squared a, and so that sine squared 2a, sine squared a is the same as 1 minus cosine 2a over 2. So if we use that expression, we can come back and plug that in, so that now we have half, this half here being pulled out, 1 minus cosine of 4x, twice the 2x obviously there, times e to the power 2x. And so we can now go ahead and say, okay, that's the same as the half times the integral of e to the power 2x, when you multiply this e to the power 2x times 1, minus a half of e to the power 2x integrated times cosine 4x. So we take this is, the first integral is a straightforward integral. The second integral, we're going to have to use a cyclical approach, and that's why I'm looking forward to that, and I have dubbed this integral, the initial integral, as I. And so that our first integral here is the same as a quarter e to the power 2x minus a half e to the power 2x times the derivative of sine of 4x over 4. So that comes from what, cosine 4x here, so that now I can use integration by parts, saying that if I have a product of v and du, then they and I integrate that, and I have uv minus the integral of u dv. So our uv is this a quarter of sine 4x times e to the power 2x minus a quarter, is a quarter here, sine 4x times the derivative of e to the power 2x, this e to the power 2x. And obviously half remains there. So let's continue. So we came up to this point, and so we can continue as follows. We use e to the power 2x differentiated is the same as 2 times e to the power 2x, and that 2 can propagate out, so that we have a half instead. So 2 times a quarter is going to be a half, and so we have the half times the integral of e to the power 2x times sine 4x. Sine 4x can be expressed as the derivative of negative a quarter cosine 4x, and the negative will come out eventually. So we've expressed this as that, and we're going to use again integration by parts. Doing that means that we can pull this negative out, so we have a quarter plus a half, the integral of e to the power 2x times the derivative of cosine 4x. So using integration by parts, as I said, our uv is going to be equal to e to the power 2x times a quarter of cosine 4x, and that becomes 1 over 8 minus 8 cosine 4x and the derivative of e to the power 2x. So e to the power 2x differentiated is going to be 2 times e to the power 2x, and that 2 will obviously interact with this 8th. But what is important is for us to know that now we're coming back to the I that we had created, right? So these two will be pulled out, and we have I here. So when we pull this out, this side, we're going to have 1 plus a quarter, which is going to be equal to 5 over 4. So a quarter I plus the I on this side. When you add, you have 5 over 4I. And so when we divide both sides by 5 over 4, we're going to have inside the bracket, I have 4 over 5 times a quarter. So the reciprocal of 5 over 4 is going to be equal to 4 over 5. And we multiply that across whatever is inside the bracket. And so we have a quarter e to the 2x minus the 4 here cancel, the 4 and the 8 here, so we have 2 remain in the denominator. So this becomes 2 times 5, which is going to be minus 1 over 10 e to the power 2x sine 2x minus 2 times 5 times 2, which is going to be equal to minus 1 over 20 e to the power 2x cosine 4x plus the integration constant. And that was the answer that was expected. It's obviously a little bit convoluted, but all the same, a very interesting problem. Is an interesting one. Nested square root signs. So as is the case, we would begin by just saying let y be equal to x, the square root of x plus 1 over the square root of x plus, and so on. So what that means is when we square y, we get x plus 1 over the square root of 1 plus, and so on. So that means that that is the same as y equals to x plus 1 over y, right? And then we can pull y onto the left hand side, 1 over y to the left hand side, so y squared minus 1 over y equals to x. And so differentiating both sides, we have 2y plus 1 over y squared dy dx being equal to 1. And that means 2y plus y squared dy can be used to substitute dx. Dealing with limits, obviously having an expression y squared minus 1 over y equals to x, that means that when x equals to 0, so what that means is y squared minus 1 over y equals to 0, implying that now when you multiply across by y, you have y cubed minus 1 equals to 0, and that means that y cubed equals to 1, so y equals to 1. Okay, and then when y squared minus y equals to x as our initial point, it means that when x equals to 7 over 2, that means y squared minus 1 over y equals to 7 over 2. Multiply across by 2y, you get 2y cubed minus 2 equals to 7y. And then when you rearrange that, we get 2y cubed minus 7y minus 2 equals to 0. By trial and error, y equals to 2 is the answer in the domain for which we're interested. Therefore, our integral here becomes the integral in the y domain of y in place of this, and then our dy, our dx was found to be 2y plus 1 over y squared dy. Limits, as we saw, 1 and 2 as the upper limit. So having arrived there, it means that now we have an integral from y equals to 1 to 2 of 2y squared plus 1 over y, which becomes 2 over 3y cubed plus the natural logarithm of y with the limits of y equals to 1 and y equals to 2. So applying, since this is continuous in this domain, we just now go ahead and say 2 over 3, 2 cubed minus 1 cubed plus log 2 minus log 1. This is natural logarithm, and log 1 is 0, and so 2 cubed is 8. 8 minus 1 is going to be equal to 7. 7 times 2 is going to be equal to 14. So we have 14 over 3 plus the natural logarithm of 2. And that was the answer that was being sought for. Problem 18, which is the definite integral from x equals 0 to x tending to infinity of x plus 1 to the power 4 times e to the power negative x squared. Now, I don't know about you, you may have a different solution, but for me, the initial inclination is just to go ahead and expand the x plus 1. Because if you try to substitute for this, then you're introducing complexity up here. So I think we're just better served hammering it the hard way. So x, using our Pascal's triangle, I quickly run up and I'm looking for the coefficients when we have to the power 4 here. So I see 1, 4, 6, 4, 1 as what we would be looking for. And so our integral here becomes the integral from x equals 0 to x into infinity of x to the power 4 times 4x to the power 3 plus x plus 2x squared plus 4x plus 1 times e to the power negative x squared. And so we can multiply that across. So we have the integral within the limits that we've mentioned of x to the power 4 times e to the power negative x squared plus 4x cubed times e to the power negative x squared plus 6x squared times e to the power negative x squared plus 4 times e to the power negative x squared plus e to the power negative x squared. It doesn't pay to work each independent part of the polynomial. We could just use a general formula to find how to each part of this long formula. First, we need to know that the base integral of e to the power negative x squared from x equals 0 to infinity is half the Gaussian integral because it's symmetrical about x equals to 0. And so that is half of the square root of pi. So knowing this, we can now go ahead and try to solve this. We're going to use a general expression. So we're going to use x to the power n times e to the power negative x squared as something that we can base to solve our problem. So we can express this as x to the power negative 1 times the derivative of obviously x times e to the power negative x differentiated, it's a derivative of e to the power negative x squared negative. And so using that, we can bunch one of the x with x to the power negative x squared, and that product is the same as the derivative of negative a half e to the power negative x squared. Now, using integration by parts, we now have uv as negative a half x to the power n minus 1 times this e to the power negative x squared. Limit x equals to 0 to infinity plus half the negative and the minus that the original negative there amounts to a plus here, half the integral from x goes to 0 to x and infinity of now e to the power negative x squared times the derivative of x to the power n minus 1. So as you can see here, as n tends to infinity, this part goes to 0, and this expression actually goes to 0 at that point. When x tends to 0, this also tends to 0. So this part fizzles out, and we have a half the integral from x equals to 0 to x to infinity of e to the power negative x squared times n minus 1, the derivative of this, times x to the power n minus 2. Pull the n minus 1 out, and we have n minus 1 over 2 times the integral of e to the power x, e to the power negative x squared times x to the power negative 2. And we can repeat that so that we have now n minus 1 over 2 times n minus 3 over 2, and so on until we arrive at the base integral of the integral of x to the power negative x squared. So it's very crucial there to see that that only happens when n is this n amounts to when this n minus 4 or this residual x value goes to 1. So let's see how that happens. Our previous formula brought us to this point, and it's obviously easy to see that when n is even, there will come a point when this part becomes, the x power part becomes 0, and this becomes 1. So in that event, this integral becomes root of pi over 2, and so when n is even, we do have n minus 1 over 2 times n minus 3 over 2 all the way to a half, all the way to square root of pi over 2. When n is odd, however, there'll come a point when this part here just becomes x, and so when we have x times this, it means that that's the same as just the derivative of e to the power negative x squared. And so instead of a Gaussian integral, we get an integral that now amounts to e to the power negative x squared with the limits applied here. So the final part here becomes actually 1. So that is the scenario when n is odd. So coming back to our problem here, we do have odd and even terms, and we'll use our general formula now to plug away, right? So with x to the power 4, we have 3 over 2, 1 over 2 times root pi over 2. The power 3, we have the constant of 4, and we have 2 over 2, 1 over 2 times 1. Squared, we have 6 as a constant here. We have half root pi over 2. And then 1, we just have half times 1. And obviously, with 4x, we have 4 times a half times 1. And then the e to the power negative x squared times 1 amounts to just root pi over 2. We can collect the root pi terms. So here we have 3 root pi over 8. Here we have 1 over the 2 cancels with 6. Here we have the 3. So we have 3 root pi over 2. And then here we have root pi over 2. So bunching those together with 8 as a common denominator. And then here we have obviously 2, because the 4 in the denominator cancels with the 4 here. And then here we have 2 as well. 4 divided by 2 is 2. So 2 and 2 we end up getting 19 root pi over 8 plus 2 plus 2, which is 4. And that was the answer that was being sought for. So it's a little bit complicated and intricate, but it just takes one to have that toolbox, knowing when n is even, when n is odd. If you knew that from the very beginning, it's just very easy to power through the problem. But here what we're trying to do is just to lead you into this bag of tools. We're just not going to solve the problems without some guidance on what kind of tools you'd want to use. Okay, so let's continue. So problem 19 is an interesting one. So it's a product of the cosines of 3x, cosine 5x, cosine 7x. So this integrated within x equals 0 and pi over 2. I'm going to use cosine a plus b being equal to cosine a cosine b minus sine a sine b, and cosine a minus b being cosine a cosine b plus sine a sine b. When you add those, you see we have cosine a plus b plus cosine a minus b equals to twice cosine a cosine b. So that allows us to now tackle the first product, because now we can choose 5x to be a and 3x to be b, so that we have our integral becoming half the cosine 8x, which is 5x plus 3x, cosine 2x, which is 5x minus 3x, obviously all in bracket times cosine 7x. So now you have half the integral from x equals 0 to x equals pi over 2 of cosine 8x times cosine 7x plus cosine 2x times cosine 7x. Now using the same process, where now we have again half times half, which is now a quarter, 7x plus 8x becomes 15x, so we have cosine 15x. 8x minus 7x is x, so cosine x. Cosine 2x plus 7x is going to be equal to 9x. 7x minus 2x is going to be equal to 5x. So now we have the best functions, trigonometrical functions. So what we can now get out of this is we have a quarter. Cosine 15x integrated is 1 over 15 sine 15x. Cosine x integrated is sine x. Cosine 5x integrated is 1 over 5 sine 5x. Cosine 9x integrated is 1 over 9 sine 9x. Now applying the limits, the beauty about this is sine of 0 is 0, so the focus really will be on the upper limit. And also, since these functions are continuous throughout this, we don't really have to do a lot of work investigating how to approach the limits. So sine of 15 pi over 8, that means this is actually where the trick is. Sine of 15 pi over 2 is going to be equal to -1. The rest are just going to be equal to 1. Why? Because this is same as sine of 16 pi over 2 minus pi over 2, right? And that is in the quadrant where the sign is negative. It's on the lower side. But the rest, sine pi over 2 is 1. Sine 5 pi over 2 is the same as sine 4 pi over 2 plus pi over 2. So this is 1. And this sine 9 pi over 2 is the same as sine 8 pi over 2 plus pi over 2. So these other ones are 1. This one here is just going to be -1. So we have -1 over 15 plus 1 here plus 1 over 5 plus 1 over 9. Times a quarter, obviously. So we have a quarter, common denominator is going to be 45. 45 divided by 15 is going to be 3. 3 times -1, -3. 45 divided by 1 times 1 is going to be 45. 45 divided by 5 is 9. 9 times 1 is 9. 45 divided by 9 is 5. 5 times 1 is 5. So adding all that up, we get a quarter times 56 over 45. 56 divided by 4 is the same as 14 over 45. So that's the answer that we were looking for. If you have any question, feel free to reach to us. We'll be very much glad to guide you along. Problem number 20, which is actually a very interesting problem. I enjoyed solving it. So we have the integral from x equals to -1 to x equals to +1 of e to the power 2x sine of the hyperbolic sine of x. And what I would do is, because when you see a problem that has the same extent in negative and positive extent, they're trying to see how you can approach the negative and the positive side. And not always, but I always feel that's what they're looking for. So what I did was to split my problem in the negative domain and the positive domain. So we have the integral from x equals to -1 to x equals to 0 of e to the power 2x of sine of the hyperbolic sine of x. And then we have the positive side as well from 0 to 1, right? And then I would like to color code, so I have the blue integral for the negative side and then the green for the positive side. Now let's just focus on the blue for now, because that's where I think we need to pay more attention. So the blue integral means that if we set x to be equal to -u, that means that dx du is -1, and so dx is equals to negative du. And so when we also substitute x with u, we have the negative being the integrand becoming negative e to the power -2u sine u. Why? Because the negative propagates through the hyperbolic sign and the sine until it comes out. So plugging that in, we have this negative and this negative interact with one another. So at this point, we don't have any, it's positive. But now to flip the limits, we have to introduce a negative. So we have now negative, the integral from 0 to 1 of e to the power -2u sine of hyperbolic sine of u. So with this expression in mind, we would like to now bring it up here so that we are now looking at the same domain of x equals to 0 to x equals to 1. Okay, so this is what we had initially, right? And now plugging in -1, the integral from x equals to 0 to 1 of e to the power -2x sine of hyperbolic sine of x plus this integral from x equals 0 to 1 of e to the power 2x sine of the hyperbolic sine of x. And so we can now bunch things together, and so we have 2 times the integral from x equals 0 to 1 of e to the power 2x plus e to the power -2x. This -2x comes from here over 2 times sine of the hyperbolic sine of x. This expression here is the same as there's minus here. This expression becomes sine hyperbolic sine of 2x times sine of the hyperbolic sine of x. Now expanding the hyperbolic sine of 2x amounts to twice sine hyperbolic sine of x, hyperbolic cosine of x, times obviously sine of hyperbolic sine of x. The 2 and the 2 here becomes 4, obviously. That's where the 4 came from. So having arrived here, we can now do a couple of things. So the first thing I'll see here is this part here is the derivative of negative cosine of hyperbolic sine of x. And we can use integration by parts, which we know always that if you have a product of function v and the derivative of function u integrated, you have uv minus the integral of the product of function u and the derivative of v. So that becomes now our v is hyperbolic sine of x, our u is negative cosine of hyperbolic sine of x, so that multiplied together we have negative hyperbolic sine of x times cosine of hyperbolic sine of x with the limits applied appropriately, minus keeping the constant for here, the integral from x equals to 0 to 1 of our u is negative cosine hyperbolic sine of x, negative cosine hyperbolic sine of x times the derivative of hyperbolic sine of x. This derivative here becomes cosh, or the hyperbolic cosine of x, and that now is important, but also noting that this negative and negative interact to form a positive here. Okay, so this expression here is the same as the derivative of sine of the hyperbolic sine of x, which is crucial because now we have a derivative under the integral sign. So this means that, and so the integral is obviously an antiderivative process. So what we're doing here is these two processes will cancel each other, and we have this function sine of the sine of hyperbolic sine of x with the limits applied to it, and these functions are continuous within this domain. So we have 1 substituted to whatever we've gotten here, minus 0 substituted, and very important to see that hyperbolic sine of x is e to the power x minus e to the power negative x over 2. So when x equals to 0, hyperbolic sine of x becomes 0. So this part goes to 0. Similarly here, this part goes to 0 on the lower side, and sine of 0 is 0. So we are only left with the 4 times sine of hyperbolic sine of 1 minus 4 hyperbolic sine of 1 times cosine of hyperbolic sine of 1. And that is the answer. You could try to simplify it, but I think that's the simplest we could get. So that actually marks the end of all the 10 problems spanning problem 11 to 20 of the regular season MIT Integration B 2025. If you have any question, we look forward to hearing from you. If you have any suggestions, if there are any errors, we welcome corrections. But you know what we do here, we just do enjoy solving these mathematical problems. If you share in this passion and in this hobby, feel free to reach out to us. But also, if you don't mind, subscribe to our channel. If you also don't mind, please share and also like our video. Till next time, bye bye.